Let us consider two reactions. We are going to nitrate benzene by using a mixture of concentrated nitric acid plus sulfuric acid at a temperature of 50 to 60 degrees centigrade. The compound form is nitrobenzene. When you do the same reaction over nitrobenzene, that is, the starting material is nitrobenzene, and we are nitrating the nitrobenzene further, that is a mixture of concentrated nitric acid and sulfuric acid at the temperature of 50 to 60 degrees centigrade. The product is metadinitrobenzene, NO2, that is, the next NO2 comes at meta position with respect to the initial one. Now, if we nitrate toluene with the same nitrating mixture, we get a mixture of two isomers, orthonitrotoluene and paranitrotoluene. Here CH3, this is ortho position, here NO2 comes, so this one is orthonitrotoluene plus another isomer form which is paranitrotoluene. So what is the reason behind this difference? Let us consider any electrophilic substitution of benzene. Here benzene, and already a substituent, already a group is present which is say Y, and we are doing electrophilic substitution over that compound. So E plus is an electrophile. So what happens if it comes in ortho position, then the pi bond comes to attack this electrophile to form this cation. The positive charge comes over the carbon which is bearing the substituent already present. Now this electrophile comes above the plane, and the hydrogen which was already present goes to below the plane with respect to the plane of the benzene ring. Then some resonating structures we can have, and that is this pi bond shift to this carbon, this bond, to form another resonating structure. The positive charge comes here, this, and that's electrophile present. Another resonating structure can also be formed when this pi bond shifts to this, between these two carbon atoms. So another resonating structure is double bond comes here, and positive charge shifts to this carbon. So these are the resonating structures if the electrophile comes in ortho position with respect to the substituent already present. Okay, now let us see what happens if this electrophile comes in meta positions. Here the compound, this electrophile, meta positions, this position is meta positions, so bond attacks here to form this cation. Since the bond breaks from this carbon, so the positive charge comes on that carbon atom, and electrophile added to this carbon. Next, the resonating structures, we have this bond shifts here to form another resonating structure. Positive charge shifts here, double bond, electrophile, and hydrogen. Next, what happens? This bond shifts to over this bond. So another resonating structure. Here positive charge comes. Okay. Now let us see what happens when the electrophile comes in para position. substituent, electrophile, para position means this position, this bond breaks from this carbon, the positive charge comes here, electrophile above the plane, and the hydrogen already present was in below the plane. The next resonating structure, okay, the next resonating structure will be electrophile, hydrogen, double bond, and that substituent. Now let us consider the stability of the resonating structures formed from ortho, meta, or para positions. And the electrophile comes in ortho or meta or para positions. Let's see the resonating structures here in ortho and para positions. If the electrophile comes in ortho or in para position, then there is a resonating structure in both the cases where the positive charge lies on that particular carbon which is bearing the electrophile. Okay, in meta position no such resonating structure is present. Now if Y is an electron donating group, that is, if the substituent present in the benzene ring has plus I inductive effect, then it will push the bond pair electrons towards this carbon which is carrying a positive charge. So that will make some reduced in positive charge on that carbon atom. That is, this factor will stabilize this two particular resonating structures. Okay, if Y has plus I inductive effect, it will push the bond pair electrons to the carbon which is carrying a positive charge, and the positive charge will be reduced, so it will increase the stability of this particular two resonating structure. So here in ortho and para position, if Y is an electron donating group, that is, if Y has plus I inductive effect, then these two particular resonating structure has some stabilizing factors. If in meta position no such stabilizing factor is present, that's why if Y has plus I inductive effect, that means in case of a toluene, CH3 group has plus I inductive effect, we know. So in presence of CH3, the incoming electrophile, that is here NO2 plus, which is formed by the reaction of concentrated nitric acid and sulfuric acid at a temperature of 50 to 60 degrees centigrade, that incoming electrophile comes in ortho and para position, because in meta position no such extra stability is achieved. But in ortho and para positions, two particular resonating structures are formed where it is getting some stability by the plus I inductive effect of the substituent CH3. Okay, so what we know, if the substituent already present in benzene ring has a plus I inductive effect, then in that compound the electrophilic substitution, in case of electrophilic substitution reaction, the incoming electrophile will go to ortho and para position with respect to the already substituent present. Okay, now what happens in case if this CH3, if this compound or if this group which is already present has a minus I inductive effect, like NO2, you know, NO2 group has minus I inductive effect, that is electron bond pair electron pooling effect. Now if it withdraws the bond pair electrons towards itself, making this carbon electron deficient. So where the carbon is carrying a positive charge and Y present has minus I inductive effect, then it will destabilize these particular two resonating structures by withdrawing some electrons, some negative charge from where? From a carbon which is already electron deficient. Okay, so that will make these two particular resonating structures very much unstable. That's why if Y has minus I inductive effect, the incoming electrophile will not have any tendency to follow this or that pathway, will not go to ortho or para position, because if it go in ortho or para position, then two particular resonating structures will be formed which will be very much unstable as the minus I inductive effect of the substituent already present. Now in meta position, no such destabilizing factor is present. That's why if Y has minus I inductive effect, then the incoming electrophile will go to meta position with respect to the substituent already present. Okay, so if NO2 group, the substituent present in benzene ring, if it has plus I inductive effect, then it will be ortho-para orienting, that is, in presence of that substituent, the incoming electrophile will go to ortho and para position. And in case of, if this substituent has minus I inductive effect, then it will be meta orienting or meta directing. It will direct the incoming electrophile towards the meta position. Let us consider a reaction when phenol is nitrated, that is, if we add a mixture of concentrated sulfuric acid and nitric acid at a temperature of 50 to 60 degree centigrade, what happens? Okay, what will be the product? The product we know is 2,4,6 trinitrophenol, 2,4,6 trinitrophenol, and the compound is also known as picric acid. So why this happens? Which is an electron donating group. Now from the mixture of concentrated sulfuric acid and nitric acid at a temperature of 50 to 60 degrees centigrade, we know this is a nitrating mixture. The electrophile generated is NO2 plus. Now NO2 plus, the pi electrons attached to that NO2 plus to form the compound, but what we expect, since which oxygen has a lone pair electron, and that lone pair can easily get delocalized, as the lone pair is in conjugation with the pi electrons of benzene, the lone pair can easily get delocalized into the benzene ring through resonance. If it gets delocalized through resonance, how it happens? It makes a double bond here and pi bond shifts to this carbon to form a resonating structure where oxygen, where a double bond is formed, oxygen is carrying a positive charge, carbon is carrying a negative charge, and these two double bonds remain intact. Next resonating structure is where this negative charge makes a double bond and the bond breaks to form the negative charge on this carbon to form another resonating structures. Here it remains same, the double bond remains same, here a double bond is formed and the bond is broken to form a negative charge. This one is another resonating structure, and another resonating structure is also formed where this negative charge makes a double bond and this pi bond makes a negative charge. So the next resonating structure is this. Now phenol is actually resonating hybrid of all these resonating structures. So if phenol is present, all these resonating structures are present equally. Now we can see that in these three particular carbon atoms, on these three particular carbon atoms in 2, 4 and 6 position, with respect to which group a negative charge is accumulated. If the negative charge is accumulated, the electrophile can easily come to these three positions once at a time. Okay, that's why at a time 3 NO2 plus comes to these three positions, 2, 4 and 6 positions, only due to the presence of these resonating structures in benzene, in phenol. Okay, that is why here a 2,4,6 trinitrophenol compound is formed. The same thing happens if we add the nitrating agent or the nitrating mixture in aniline. Again aniline has, if you nitrate it by giving a mixture of concentrated nitric acid and sulfuric acid at a temperature of 50 to 60 degrees centigrade. The compound formed is 2,4,6 trinitro-aniline. Okay, here NO2, NO2 and NO2. The same thing happens here. Here oxygen has lone pair electron which gets delocalized into the benzene ring through resonance. Here nitrogen also has lone pair electron, and which is also in conjugation with the pi electrons of benzene, so it can also get delocalized into the benzene ring to form these resonating structures. A pi bond. Similar way to form another resonating structures, as we have seen in case of phenol. The same thing happens here. Here a double bond, negative charge, double bond. Again negative charge converts into double bond converts into negative charge to form another resonating structure. Okay, here we also can see that 2, 4 and 6 positions with respect to the substituent NH2, negative charge is accumulated. So if we nitrate or if we give any electrophile in the solution, the electrophile will go to these 3 positions once at a time, okay, as there some negative charges are accumulated. Now let us consider a reaction. In case of nitration of phenol, NO2 plus a mixture of concentrate nitric acid, that is concentrate HNO3 plus H2SO4 at a temperature of 50 to 60 degrees centigrade. The compound formed is 2,4,6 trinitrophenol. But if we nitrate chlorobenzene Cl, the same nitrating agent, the compound formed is a mixture of orthonitrochlorobenzene plus paranitrochlorobenzene. Okay, but again chlorine is more electronegative than carbon, so chlorine will shift the bond pair electrons towards itself, so it is deactivating group. It has minus a inductive effect, so it supposed to be a meta orienting, but here it is acting as ortho para orienting group. Okay, so why that happens? First of all, which in case of phenol, delocalization occurs. Delocalization of lone pair of oxygen occurs into the benzene ring. How it happens? In benzene, 6 carbon atoms are there. All have alternate double bond and single bond. And all have a hydrogen atoms pair present. And here in case of phenol, here oxygen is present, and with oxygen and hydrogen atom is also present. Now here the oxygen has lone pair electron, and that lone pair electron present in 2p orbital. And in case of carbon, as it has formed 3 sigma bonds, so it is sp2 hybridized, so pz orbitals remains unused. So here the pz and this p orbital present in parallel position. So here this one is from 2p orbital, and this orbital is also a 2p orbital. So here 2p 2p lateral overlapping occurs, and that's why a double bond is formed. When here a double bond is formed, this pi bond shifts to this double to make this double bond, and it shifts to here, and this pi bond ultimately forms a negative charge with this carbon atom. That is how this lone pair gets entered into the benzene ring through resonance. Here double bond occurs as it is due to lateral overlapping between a 2p orbital of oxygen, a filled 2p orbital of oxygen with another 2p orbital of carbon. But in case of chlorine, when it is attached to benzene, when chlorine attached to benzene, let's see what happens. Here hydrogen, 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 and here chlorine. Now this chlorine has also a lone pair, and this carbon also has a pz orbital, but this lone pair is in 3p orbital, and here it is in 2p orbital. Due to energy difference between two orbitals in different energy level can make a head-on overlapping, but when a lateral overlapping occurs, they must or they should have in same plane. If they have different, if those orbitals are in different energy level, in case of 2p it is in lower energy level, and in case of 3p it is in higher energy level, so lateral overlapping is not effective. Okay, that is why this delocalization is very poor. In case of phenol or in case of aniline, oxygen or nitrogen, the lone pair of nitrogen is also in 2p orbital, and in carbon it is 2p. So in case of aniline, the lone pair can easily get delocalized into the benzene ring, as here 2p 2p lateral overlapping occurs between nitrogen, lone pair of nitrogen, and the carbon, 2p orbital of carbon. In case of aniline, in case of phenol, delocalization is very effective, but in case of chlorine, chlorine still have lone pair electron, but that lone pair is present in 3p orbital. So here the energy gap is there between the 3p orbital of chlorine and the 2p orbital of carbon. So lateral overlapping is not so effective, and that's why delocalization is also not so effective. That's why chlorine cannot activate benzene ring in such extent that 3 electrophile may come at once. As we see in case of phenol or in case of aniline, the delocalization of lone pair of nitrogen or oxygen makes the benzene ring highly electron rich or highly effective or highly activated towards the electrophilic substitution reaction, so that electrophiles may come at once in every possible positions or in every available positions. But in case of chlorine, no such happens, no such factor is there, as the lone pair cannot get effectively delocalized into the benzene ring. So lone pair cannot activate the benzene ring in such extent. Okay.